question.
Oh, shit. Random sample of size 64 is taken from a normally distributed population that has standard deviation 4. What is the probability the sample mean will take on a value that is within 0.75 of the population mean?
True.
So
You started it a different way than I do.
the formula you just need to know for this guy is z. It's x bar minus mu over standard deviation over square root of n, right? You probably remember that formula way back from stat 1, if you took AP stat or if you took 2023 year. So the question is, what's the problem? Here's what's nice. Did they give you the mean? Did they give you mu? It might be a little unsettling at first if they didn't give you mu, right? You're thinking, oh shit, how can I do this problem? They don't give me mu. Look, they don't care that what the mean is, nor do they care what the sample is. They just care that the difference is no more than what? 0.75. No more than that. Yeah. No more than that in either direction, right?
That's not a question. Just, I mean, it's the same thing, but why do you start with the mu minus 0.75 on either side? Well, like for me at least, it usually makes sense when it's saying.
Like this, you mean?
Yes. No. Well,
I think this is what.
No, what I was usually doing.
I think I know what you're saying.
What I was doing here. What I would usually put, and I was kind of wondering because I see in the textbook they usually do this, but if it says probability sample mean will take on a value that is within 0.75 of the population mean, I would just go straight and I would go straight here and just be like, here's the sample mean minus the population mean and 0.75.
And absolute value first.
Yeah, 0.75. Oh, I did absolute value first.
Oh, I see.
Yeah.
Yeah, this is fine. Yeah, sure. These are equivalent statements, so
Yeah, I just didn't know what's the thinking behind this, because it doesn't make sense to put it like that.
it doesn't make sense to you to put it like that?
I mean, I know you can.
Right, well, I mean, these are all equivalent statements. So this is like saying, where's the bathroom? Do you know what the bathroom is? Where can I find the bathroom? These are all statements that mean kind of the same thing,
I guess
right?
so.
So x bar minus mu being less than 0.75 is the same thing as x bar minus mu being less than 0.075 but greater than negative 0.75. And then also if I add mu to both sides, I get x bar is less than mu plus 0.75.
Does this belong to anyone here?
Not me.
Thank you.
Hey, how's
So-
it going?
So going good. mu minus 0.75. These are all equivalent statements. So while you might want to start here, I just say start here. Doesn't matter. No one's going to dock you points if you start here or here or here.
True.
It seems on the test, this person, whoever wrote this, but again, I probably could have written like this, and I don't think I would have any points taken off. That'd be rude, is a word that would use to describe points being taken off of that. This is an equivalent statement to that, mathematically equivalent. Cool.
Cool.
All right. So we're curious to know. What's the probability. Is that right?
Number one.
Probability.
Mm-hmm.
What's the probability that this difference is in this envelope of negative 0.75, larger than 0.75? Well, we don't know what x bar is, we don't know what mu is, but we don't care. We just care to know what z-score corresponds to this outermost value. You can look at a normal distribution. This is the mean mu. And we care to know how much area corresponds to, do it right there. How much area corresponds to this envelope? How much area would be in that envelope, given the information that we're given? Well, we're going to take this z-score and set it equal to, or we're going to take not the z, we're going to set our z-score, z equals 0.75, or just taking this value and putting in the numerator of this x bar minus mu value. We know that sigma, the standard, well, I put variance. I don't know if this is how he writes it. Normal, mu, comma, variance.
Yeah, he'll do that.
Okay. So our standard deviation is 4, and our sample size, we're told, I didn't write it down, but our sample size that was given to be 64. So we're looking over the square root of 64. We're basically trying to figure out what z-score does this correspond to. That is, what z-score is.
And you only do that.
Corresponding
You
to
only do that if you're talking about the sample mean, not necessarily if it's just the.
One observation.
Yeah, one observation.
Yes, this is a sample mean. So usually you might see a formula. So when you first learn this formula, you just see divide by sigma. We're talking about one observation. One observation being a sample size of 1, meaning you're dividing by the square root of 1. So you don't see it there. But yeah, this is for sample means. And I think sample means are going to be a bigger deal for this class than just one observation. But yeah, you make a good point that this all stems from the z-score that you learned about.
But variance is actually equal to that, and you just like take the square root.
Okay, so 4 over square root of 64, we have 0.75 over 4 over 8. 4/8 is 1/2, but to divide by 1/2 is to multiply by 2. So this corresponds to a z-score of 1.5. At which point, you either use a calculator or you use the table to figure out where negative 1.5 and 1.5 correspond to on the normal curve. Now,
right here.
good. Do you guys use a graphing calculator? Are you allowed to use a graphing calculator?
Yes.
Yeah, we are.
I can show you how you can do it on the graphing calculator. Some people prefer that.
It gives us a table.
Yeah, mine was the table.
So
Okay.
the table's pretty.
So 1.5 corresponds to 0. And be careful here. This is 0.668 in the right-hand tail. Can you scroll for a second?
Mm-hmm.
In the right-hand tail. So this is telling us 0.06668, right?
0.0668.
Okay.
1.5 is, yeah.
Oh,
0.668 is here.
I see.
That means 0.0668 in this tail.
Mhm.
You know, the total area under the normal curve is 1, so you just add these numbers up and subtract it from 1. So this would be
1 minus 2 times.
1 minus 2 times
Okay.
0.0668, or that's about 0.87.
Okay.
And your friend put down 0.8664, and seemingly nothing wrong. Nothing was counted as wrong. Good?
Good.
Yeah.
Now, the next question is, so it's all points something out here. We were given a bunch of numbers. We were given this, we were given the standard deviation. We weren't given mu, we weren't given x bar, but we were just concerned with the difference anyway. If you were given mu and you were given a sample bar, then you could find, x bar rather, I'm already so tired of that formula. You could figure out x bar minus mu just by being given those things. But if you're not given sigma, or you're not given square root, then you might be thinking, well, how can I do the problem? It might be because they give you some other information. So in this next problem, part B, says, how large a sample? Immediately you should think, okay, well, we don't know n. How large a sample must we choose so that the resulting probability would be 0.95? That is, this resulting envelope would now be 0.95. Ooh, looks like an 8. Okay? So we're kind of doing this backwards. We're backtracking.
Okay.
We want this envelope to be 0.95. A lot of people think, well, what the fuck do I do now? Well, what does that mean if there's 0.95 in the middle? How much is in each tail? 0.025. And that means you do what? What do we want to do with this information?
So then you're going to find out the z
We're going
table.
to look it up in the table. So 0.025,
1.96.
1.96.
Yeah, right there.
So this is the z-score. We have 1.96 equals x bar minus mu over sigma. We know is again 4. We don't know square root of we don't know the sample size. And we want the difference to be how large would the sample in order to be required probably 0.95 that the sample mean would be within 0.4. So we're not using 0.75 this time as part A said. It wants the deviation, or the deviation between x bar and mu to be 0.4. At this point, we just solve for n. So we're going to, this is the same as 0.1 equals 1.96 squared in. Did I fuck that up somehow? What the hell? Yes, I did.
Yes.
Over squared in.
Yeah.
Okay.
Mm-hmm.
And then squared in
Yeah,
equals
you're right. Never mind.
19.6. Okay. We then square both sides and get n equals someone squared 19.6 for me.
Right here, then. There's-
I'm gonna go with
384.16 when you round up.
you always round up. So this is 384.16. Actually, doesn't matter. You always round up whatever the because let's put it this
Because we
way.
need the whole sample, so.
The whole sample, but then why round up, right? I agree that you need a whole sample. You can't have you can't have half a person or whatever. Why always round up? The reason for this is if you round down, that means the error would be what?
Larger.
Yeah, that'd be slightly larger, slightly over the error that we don't want, or we want to be in the envelope.
It's degrees of freedom that you round down, though, right?
Depends on what context we're talking about. We'll get there. Yeah, we'll get there. All right, so it means our sample size needs to be 385. Cool.
So where's
Cool.
this? So did you not even like? I guess you even finish it.
I don't even know. That's weird. Yeah, I guess he didn't finish it, but he still got credit. It's lucky. Okay. T has a T distribution with new degrees of freedom. Prove that T squared has an F distribution. Identify both degrees of freedom for the F distribution. Holy shit. I don't know this one. Can you go over proving that the square of the T distribution is the...
They give us some formulas with what the T distribution is
Yeah,
and
so these are the formulas we have.
all that. So it's T is Z over the square root of W, which is a chi-squared divided by...
So T is equal to Z
Z
over
over square root
of W
W
Or
divided by V. All in the root.
onto the root.
Where are you seeing now?
All in the
So
bottom.
T is a random variable that is equal to the Z random variable, which is divided by square root of W over nu.
So,
And these are
T
constant.
squared, if T has a distribution, T squared is F distribution. Okay, so
Oh,
you
you're supposed to
square
prove it
it.
using, do you prove
I
this
know
using
this one.
MGS?
So if you square it, then you have a Z squared on top, which is also a chi-squared.
Right.
And that's a chi-squared with 1 degree of freedom. So that's a W divided by 1, which is...
Would you write like this chi-square 1?
He just does like a little subscript, I believe.
Oh, yeah.
Usually just
Yeah.
subscripts, yeah. So it's a chi-squared on top. Z squared is a chi-squared 1, and on the bottom, that's also chi-squared V. W is a chi-squared
Oh, W
V.
is also a...
And F is
Very
a chi-squared divided by its degrees of freedom over another chi-squared divided by its degrees of freedom.
Why is this considered a...
That's what it's defined as. It's
Oh.
just W. He says is a chi-squared
Okay.
and divided by its degrees of freedom.
So W is also distributed chi-squared with new degrees of freedom?
Yes.
Okay. So that means...
So that means that the Z squared is a chi-squared with 1 degree of freedom.
And
which
since
you can
F,
find.
an F variable is a ratio of 2 chi-squared variables.
Exactly. So you can just divide it by 1.
Right. You could say this is Z squared over 1 and W over nu.
Although there's some more like complicated problems in the homework.
Sure, we can look at some other ones.
Yeah. Where do you want to?
I have to open up Simon one real quick. But yeah, we can go on.
Yeah, these are the first problems. He said the first problems would be the easiest. So
The first ones are usually pretty easy, but that's because it's like really like simple, straightforward stuff, and then
yeah.
A fruit farmer wants to compare 2 spray that kill insects damaging to his crops. The farmer sprays 200 trees with spray 1 and another 200 trees with spray 2. At harvest time, the farmer finds 186 trees spray with spray 1 or insect free, while 164 trees spray with spray 2 or insect free. Estimate the difference in proportion of insect free trees and place a 2 standard deviation bound in the estimate. Okay, so this is what let's have a broader conversation. You're gonna have, as a chart that I'll write down, I guess. Oh, wait, so bigger.
Do you know what problem you want to do next after that?
That's not what I want to do.
Okay.
Okay, so you might be, you're probably not asked to do any significance tests, right? Are you? No significance tests, just
significance not yet.
just probably exam 2, but confidence intervals you will.
Yeah.
All right.
Yeah.
Considerably.
So we're talking about mean. These are X bar. These are the things you're going to see. You might see for 2 mean, you might see mu1, mu2, or X bar 1, X bar 2. Portion, you might just see P, and then you might, or P and P hat, P1, P2, P1 hat, P2 hat. So that's the things to keep in mind. And you also have to keep in mind the scenarios under which you use these. When we're talking about SAT scores, what we have 500 students at Buchholz High School that scored an average of 322 on the SAT math. That's actually a really abysmal score, but whatever. That's talking about a mean score. Versus if I say how many people are going to vote for Obama in the next election, which, well, not possible because it's only 2 terms. But say, suppose that the 23rd Amendment, or no, the 22nd Amendment. The 22nd Amendment is what limits the number of terms a president can have. If we repealed the 22nd Amendment and Obama could run for a 3rd term, what percentage of people would vote for him? That would be a proportion because we're looking at a yes or no question. Did this person vote one way or the other? This way or that way. It's binary data here. Versus Means, we're talking about scores, we're talking about calories, we're talking about...
Hey, was there any Mirror Mouse left in here?
Yes.
Yes.
Yeah.
Somebody was trying to ask whose it was.
Oh, check the front desk.
Yeah.
Yeah, check the
Yeah.
front
I think
desk.
she left out. I don't know if it's her or the girl in the black. I'm not sure though. Yeah, she was sitting there and she's gone.
Oh, no, like in the room.
No, but
Well, she found
she
it,
found it.
and then she asked us. We said we didn't know whose it was, so she just, I think,
she might have traded
yeah.
up there though. Okay, so you're gonna have to identify scenarios based on, there will be very, some keywords here. We're talking about trees that are going to be insect-free versus not insect-free. So that's binary data. It's either insect-free or it's not. It's a yes or no question. So, and we have spray 1. For spray 1, we had 186 trees that were insect-free out of 200. So that would be 92%, 93%. Okay? Spray 2 worked how well? It was 164 out of 200. This is 0.82. So the question is, it wants to know what's a good estimation for the difference. Well, you can always try the point estimate. The point estimate is just taking the difference of these two, and that will be important. We're going to call this, by the way, P1 hat and P2 hat.
I'm gonna look at this part.
Okay.
Alright.
So what does P1 hat and P2 hat mean? P1 hat, by the way, this hat just means what it's estimated to be. We don't know what, if we were to spray this on millions and billions and trillions of trees, what true proportion would come out of that? This is only a sample of 200 trees, and it seems to be 0.93, pretty good estimate. Of course, that estimate gets better and better the higher, the more. It's just as easy as P1 hat minus P2 hat equals 0.11, and that's called a point estimate. But statistics is not just analyzing a single point, it's analyzing a range and how likely that range is, or how likely it is that the true proportion is going to be, or the true difference in proportion will be in that range. So the way we figure that out is using a, there's going to be a bunch of formulas that I should probably put in this box. The one that we're going to use in question for this problem, I'll write it here, is, if I have room to, yeah, I'm going to make this box bigger. And by the way, you're going to need to memorize these. P1 minus P2 plus or minus Z star times square root of, gonna be okay?
Yeah.
P1 over N plus P2 times 1 minus P2, or I should say hat here.
Yeah, we have that right here.
Good.
Yeah.
Yeah, that's
Perfect.
provided
Are
to
those
us.
all provided? Okay.
Yeah.
The prod. Although the
It might be considered.
although the Z star, like they didn't really use that when I went through the problems, like the same things. They don't really use the Z in it. They just do plus or minus the square root of
There's
all
no,
that.
there's no Z star here?
I mean, when I did all the problems, I have to go check again, but they never multiplied it by it. It's weird,
He
actually.
has Z of alpha over 2.
Yeah.
He does have that there, but
Yeah, definitely needed.
the point estimators he didn't use. I don't know. Let me go back and check my homework. and
Sure,
see.
we'll hit it later. All right, so this is the formula we're going to use for this problem. We want to find a confidence interval. And by the way, this is the formula for the confidence interval. You should memorize it or just know where it is on your formula sheet.
Okay.
The confidence interval will be P1 hat minus P2 hat, which we know is 0.11, plus or minus Z star. What is this Z star shit? Well, we want, what are we curious to know? We're looking for a 2 standard deviation bound on the estimate. 2 standard deviation bound corresponds to Z score here and Z score here. We want to know what Z score corresponds to yeah, that's it, Z score. That is your Z score, sorry. That is its Z star is. They want a 2 standard deviation bound, that's your Z star. Basically the number of standard deviations away from the mean. They want a 2 standard deviation bound, so guess what? They want 2 standard deviations away.
Where's that come in?
They tell us this is the problem.
Yeah, they said
In the problem it says what?
It says,
It's a 2 standard deviation bound on the estimate.
we want to find an envelope. We want to find
Okay, so no. So I think I might have misunderstood what it was because like 4 said, at least in the homework I had a similar one. It actually might have been the same problem. Actually, it is the same problem. Yeah. Okay. I thought the 2 was because it was like had to do with it being on both sides.
Nope.
Okay, that makes more sense then.
Yeah.
I like it.
this will be a different number if they wanted a 3 standard deviation estimate.
Yeah,
It'd be
okay, that
3.
makes more sense now.
Oh,
I like
okay.
it. That's good.
Square root of, and then we just plug all these numbers in. 0.93 times 0.07 over 200 plus 0. So one of you guys is gonna have to crank these out. From 8 to 0.18.
Does anybody have a calculator with them? I didn't bring them.
I do.
I'm gonna use his.
Yeah, that is.
Okay, so in this case right here, on this formula sheet,
That's
That's
what we're
just-
using.
that's the Z star.
That's E star.
And it's just however many standard deviations they want.
Yep.
Oh.
Now they might say this differently. They might say they want a 95% confidence interval. And what that means is they want 95% in the middle, and what would they want in the tails?
0.05.
0.025. So it's almost
0.25,
0.25.
okay.
And 0.025 in each tail,
Gotcha.
and then you reverse look it up in the table.
So
Like
it's
this.
0.11
Oh,
plus or
okay.
minus 0.065.
That makes sense.
This guy, 0.065.
Yes.
All right. So now I want to grab your calculator for a second. Now I want to show you another way you can do this. Watch carefully. Look, I'm going to try and do this as best I can. If you have a TI-84 or TI-83, you can go to Stat, Tests. This is a, proportion or mean? This is proportion. We're dealing with a P, so this is a proportion. In fact, there's 2 proportions. So if you scroll down to 2 proportion Z interval, there's a 2 proportion Z interval. I'm going to hit Enter. We have, for spray 1, 186 successes out of 200 trials. For spray 2, there were 164 successes out of 200 trials. The problem with this is they want a confidence level. They didn't give us a confidence level, they just said some number of standard deviations. But it turns out that for 2 standard deviations, what is it?
It's 0.0228.
It's 0.0228, so 1 minus, let's see,
1 minus 2 times 0.0228.
1.
Wait, was that what I was supposed to know?
95, 1.96.
What was that coming?
Or that would just be 0.945. Calculate. And they give us, the calculator gives us the interval 0.4742, comma 0.17258. This compares to this guy, which is 0.11 plus 0.065. Oops. So pretty close. I don't think
He
any.
probably shaved off a few decimals.
Right.
So what was that part that you plugged into the calculator? You gave it,
So-
you had to find the Z-score of 2?
So
Yeah, it's a little
so-
backwards. And I recommend doing it this way if they tell you a certain number of Z-scores. But if they tell you a proportion, they tell you,
Sure.
sorry.
This is a good way to double check it. because-
Yeah.
Yeah.
So he said 2 corresponds to 0.0228. So for the confidence, you put 1 minus 2 times 0.0228.
Okay, wait, so he asked are we supposed to like write with confidence of
No,
whatever,
I don't think so. No.
Oh, okay.
So your confidence level is what's in the middle. It's your envelope. So they said a Z-score of 2. They said within 2 standard deviations. That means that's not a number you plug into this guy. It doesn't tell you how many standard deviations of confidence do you want.
Yeah.
That's something you have to find from the table and then plug into here.
It's 9544. That's probably why it's a little
9544.
Okay.
Yeah.
I'm guessing.
It's a little like it's 0.044.
No, so how do you get to that part again? Because I'm guessing there's a lot
Yeah,
more like things we can plug in there.
Definitely there are.
Because that's like I make stupid mistakes on my work.
We'll
all
do
the
that.
time.
We'll do the message.
Yeah, that's a good
We'll use this
Okay.
as we see more of them. Let me recap how I did it again. So you go to Stat, over to Tests, and then you have the first 6 or 7 or 8 of them are tests, like significance tests, which you aren't doing on this first exam.
Okay.
The second half of things on this list are intervals. And this is a 2 proportion Z interval. So I hit Enter. You tell how many successes out of successes out of trials for the first guy, successes out of trials for the second spray or second whatever treatment. Plug in the confidence level, which is going to be given to you. If it's given to you as number of standard deviations, you can do a reverse look up the table, or you can just use the formula
So
and hit calculate.
quick question: Can we use this for? So we use it for confidence intervals. It has that Could we use it for point estimation or?
Point estimation is really simple. You don't have to do anything other than find the difference between these two numbers. That's it.
Okay.
Yeah.
Well, there's like other ones where you have to use the like mean square error and like stuff like that.
Oh, okay, yeah, I see what you mean. I don't think it does mean squared error or stuff like that.
Okay. What
Yeah.
about anything that has to do
Bias?
with moments?
No, that doesn't mean anything like that.
Damn. Okay.
Yeah.
Okay.
All right, so well, I'll think if I can think of something that does, but for now, let's say no because I couldn't think of where it would be. All right, one other thing I want to say about this is let's try and interpret this. I don't know if you care to know what it means to interpret these sort of confidence intervals.
For some of them, we actually have to write.
Some sort of
Not this one, but usually we'll have to. You'll like ask
what's
if it's
Significant.
within,
Yeah.
yes.
okay.
Yeah, you say if, yeah.
Is it significant? What for any sort of proportion? We're talking about whether or not this interval captures what. Okay. We need to know if this interval captures 0. If it captures 0, that means there's not a significant difference. But basically, think of it this way. You ever heard the phrase same difference?
Mhm.
Really, or no difference? If I said, we're talking about, oh, I've got 6 eggs, well, I have half a dozen. Same difference, or no difference, right? We're talking about, if I said x was 6, and I said y was half a dozen, then x minus y would be 0, right? Well, what is this essentially saying about x and y?
They're equal.
They're equal. X and y are equal. Make sense? So if there's no difference, then they're equal, right? The difference in these proportions never at any point is equal to 0. That is, the difference between P1 and P2 is never, or at least in this interval, this 95% confidence interval, is never, it should be 0, 4, 5. There we go. This interval never captures 0. So with that in mind, it is to say that these two sprays, there is a difference. If on the other hand, these numbers could have been a little bit closer. Like I could have done, let's say, 180. And this would be 0.90, right? And if I run this stuff again, if I run this two proportions the interval again, I'll tell you what my interval is. If it'll let me. This is 180 out of 200. I get negative 0.0257, comma 0.085, whatever. This interval captures what?
It does capture 0.
It does capture 0, which is to say these two sprays are close enough. We're saying that, you know what, there's no significant difference here that we're going to say it could have just been due to natural variation of these things. This one just came up a little bit better. But the next time we run this experiment, maybe this guy's better. Next time we run, maybe this guy's better again, and this guy's better again, then it's this guy. There might just be.
You guys wrote down his notes about how he wants us to word it? He likes us to word it like a specific way.
Like,
let's see if I can-
95%
Yes.
confident that, okay.
Yeah, it's probably actually in the exam, so we'll find it. Like that one.
I don't think
He's
it's
like-
not for this question.
For that question, you don't have to, but when he asks for a confidence interval,
Yeah.
with a percent
So we
confidence.
can conclude that
Yeah.
We are 95% confident that the true difference in proportions
Is within this interval.
Or not within this interval.
is proportions is within that interval, whatever that interval was. This guy's gonna copy that better there.
Okay.
Cool.
Perfect.
Good? All right, let's try the next one. We're going to move on and we'll maybe see some more proportion stuff. The quality of computer disk is measured by, actually, can you read it to me?
quality of computer disk is measured by the number of missing pulses. Brand X is such that 80% of the disks have no missing pulses. If 100 disks of Brand X are inspected, what is the probability that 15 or more contain missing pulses?
Okay, so this is just a probability question. We're going to be doing some little bit of binomial probability. The quality of computer disks, does he really want you to use...
So
sometimes he wants to use the binomial, or the normal distribution approximation of binomial.
I think how many was the number percent?
100 disks.
Then I think we're going to be using the
Right, because you need to make sure that
it's called the Z. Well,
the normal approximation.
What was it called when you have a large
Central limit theorem.
There you go.
The quality of computer disk is measured by. Yeah. Oh, this. Okay, I see this thing. All right. So here's the deal. You could do this using the binomial theorem, but it would take a lot of work. Here's why. Let's recap binomial theorem really quickly. We've got 5 coins. What's the probability? Let's say x is number of heads. What's the probability that x is equal to 4? What's the probability that when you flip 4, these are fair coins, I'm not gonna rig these coins or anything, those are fair weighted coins. What's the probability that 4 of them come up heads? How can I do this? You might need to know this formula here. X equals K is equal to N choose K times the probability of success, the K, times 1 minus P to the N minus K. Let's kind of analyze this formula. This is a really important formula. You might have learned it for 4321, but you might have merged it since then. N choose K is just the number of ways you can rearrange these coins. Or if you have heads, 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 tails, how many different ways are there to rearrange it? Well, how many coins are there total?
5.
5 factorial over how many H's are there?
4.
4 factorial, and then how many tails are there? 1, so 1 factorial. This is another way to rearrange them. And this is like a really common, if you know me, you know I'm a math competition guy. So what kind of questions they ask on math tests? What are the number of distinct rearrangements in the capital of Florida, Tallahassee? I know this one by heart. I think it's like 86,303. 160,100. I'm going to transpose those digits, ironically. How many rearrangements are there in the word Tallahassee? Well, how many letters are there total? 11.
Then I have to count how many repeats.
Yeah, repeats. We got 2 L's. 2 factorial is just 2. We still write factorial for completeness. We got 3 A's,
2 S's,
2 S's, and 2 E's. And that would be the number of rearrangements of the word Tallahassee. Make sense? Distinct rearrangements, right? Because if I switch the E's, you won't notice a difference, right? So this pertains to the binomial theorem. What's the probability that 4 heads come about a 5? Well, that would be 5 choose 4, which would be 5. 5 factorial is what? 24 is 24. 120 divided by 24. You guys are so tired from studying earlier, huh? 5 times. What's the probability of a heads coming up at any given coin?
0.5.
0.5. How many successes do we want?
4.
What's the probability of a failure?
0.5.
0.5. Not really exciting, is it? And then we want 1 failure, so the power of 1. That's how you do this. So we have these hard drives, right? That have 80% of them. The probability of, let's say, missing pulses. This is very confusing. You have to pay very close attention to the wording. It says that 80% of the time they have no missing pulses. Am I right about that? That 80% of this have no missing pulses. So that means the probability that a given disk does have a missing pulse, it would be 0.2. Does that make sense? Yeah, so be careful of that. It's really confusing. No missing pulses is to say that it has pulses. Very confusing.
Do you have this too? So, I'm saying, do you have it with you, or
Yeah.
so you guys could, so you could get together?
Okay, so what's the probability?
Problems too. These are all homework. You go over the homework because almost all the questions are straight from the homework.
Yeah, sounds good.
So we have 100 disks. What's the probability that, does it say more than or exactly 15? Probably more than, right?
Probably more, 15 or more.
15 or more.
15 or
Well,
more,
probably
yeah.
that X equals 15, more than 15. This is a pain in the ass because what it means is we need to do this. We would need to do 100 choose 15 times 0.2 to the 15 power times 0.8 to the 85. What's this the probability of? That out of 100 disks, 15 have missing pulses, right? Well, we want to know the probability that at least 15 have missing pulses. So we have to do what? Plus, the same thing over again, but now with what?
116.
16, right? And 17 and 18 and 19, and all the way up to 100. This computation would take far too long. There's another way you could do it called the backdoor method. Rather than doing 15 to 100, you could do what?
1 minus 15, 0.
Yeah, 0 to 14, right? Because we have
Yeah.
15 included here. But even that's still computationally intensive because it's 14 different things you have to add up. So it's going to be way, 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 way too much work to do. So this is where the normal approximation of the binomial theorem comes in. That is, if n gets large enough and the probability of success is large enough, or somewhere in the middle, then we're good. So here are some conditions that must hold for you to use the normal approximation of the binomial theorem.
Okay.
I think it's n times p is larger than or equal to 15, right? Is that what they say? Have you seen these before?
Yeah.
N times P is,
You might say 10.
yeah. It's that, and we also use a correction factor.
Yeah, correlate a correction factor. Yeah. Okay, so here's what we're saying: is that the distribution of disks. Here's 80 discs, 100 discs, that it peaks right around 80. It kind of looks like a bell curve. It's not perfect. And in fact, these are actually little bars here. But it is roughly resembling a bell curve. So what we're going to do is we're going to say, well, instead of doing the probability, we're using binomial theorem, adding all these up, we're going to say this, for instance now, we know that this guy's variable x is distributed binomial with 100 trials and 0 point. Now I'm confusing myself with this 80%, 20% shit.
0.2.
I want to say 0.2 here. I think I want to
That's
say
what he had.
Yeah.
0.2 is the number of successes.
Probably.
Yeah, because you're checking how many have.
Successor.
So 15 or more have 15 missing pulses.
Right.
So it's 0.2 missing pulses.
Okay, so 0.2. But this, using you might say central limit theorem or something like this, well, is normal with mean. The mean is, well, if you have 100 hard drives and 20% of them on average are going to have missing pulses, then on average, how many have missing? On average, it's 120, right? All you do is multiply these numbers. In fact, you would n times p, which would be 20. And what's the variance? Gotta memorize it, but I'm sure it's in your chart here, right? Probably have it over here. So then you better, well, maybe it's not.
Yeah, it is.
Oh, over here. It's just good to know it. NP here and NP times 1 minus p, I believe, is your variance. No problem. Boy's bugging out. He's like looking, like constantly staring at the door.
Is it waiting for?
Anyway, n times p times 1 minus p, so we have 20 times 1 minus p would be 0.8, 0.8 times that would be 16. So the variance is 16. And we also make sure, and again, I don't know if you would dock a point for this, but you do want to make sure that NP is larger than 15 and n times p times 1.
He has, the formula he uses is that for the smaller one.
Okay.
So in this case, it would be n is greater than 9 times 0.8 over 0.2. That's the formula he likes to use.
Okay, yeah. Whichever one, yeah, as long as that, works. Cool. No problem, man. Okay, so what are we doing here? We see this is going to take a long time to calculate, so we're going to use the normal distribution instead. This normal distribution is basically superimposed on top of this and looks pretty damn close to what the binomial is. So what we're going to do is we're curious to know what's the probability that x is larger than or equal to 15. The problem with this is, and we're going to get down to the nitty gritty here. Remember how I said that these are represented little bars here?
Yeah.
I'll blow this up.
Like density functions?
Yeah,
Okay.
a mass function, right?
Do you need a better marker here?
I do. Is that better?
I could go grab one from another room.
This will work for now.
Alright.
Okay. When we take a break, I'm not getting another one, so I get a better one.
Okay.
So what's going on here is we've got a bar here, and a bar here, and a bar here. This corresponds to 15, this corresponds to 14, this corresponds to 16. Notice how the number down here splits this bar in half, right? So you might see us saying, okay, we're going to transform this to
Okay, that's what I do.
p of x larger than 14.5, because this is going to give us the whole bar. Does that make sense?
Yeah.
Or if it's, be careful here, because if I say larger than 15, I don't want this right half, so I'll say larger than 15 and a half. Make sense? So be on the lookout.
So that's the purpose of the confidence.
That's what's called the correction factor, right?
If you can remember one of them, then you know them all.
Right.
So it's like if x is greater than and equal to, then you subtract, and then it's
Tell you what, don't think of it that way.
just
Just draw this graph, right? If it says larger than or equal to 15, that means we want to include this entire bar, right? So we want this bar, and we're going to start here. This would correspond to what? 14.5. If I wanted less than 15, then I would say, again, 14.5. If I wanted greater than 15, I would say larger than 15.5. And if I said larger, or if I said less than or equal to 15, that would mean I want this bar. So I want to include if I want to go that way, so I'd say 15.5 in that way. So less than 15.5. We want to be larger than or equal to 15. So again, do we want this bar? Yes, we do. And we want it this way. So we want this entire bar starting here and going to the right. Where does this correspond to? 14.5. So x is larger than 14.5. How do we do this using the normal distribution? This is where we use that x bar minus mu shift, right? So we have 14.5 minus 20 over, this is going to blow my mind here, do I divide by sigma, which is 4. Why is sigma 4? Our variance is 16, but then do I divide by square root of 100? No.
He
I can tell
uses,
you, you divide by.
this is the Z that he uses right here.
Yeah.
Oh, okay.
But what is that? Yeah, so,
Oh, I see what you're saying.
yeah, what is square root of n times p times 1 minus p? What does n times p times 1 minus p give you? That gives you the what?
That's the standard.
That's the variance, the square root, of which is then the what? Deviation. So this formula is good to know. What am I essentially doing though? I'm using,
So you're just creating
I'm
the
doing
Z
x,
form, the
I'm
Z
doing,
formula.
yeah, exactly, x bar minus mu
Okay.
over standard deviation. But what is the mean for this binomial distribution? Multiply these two,
Mhm.
which is n times p.
Gotcha.
And what is my sigma? Well, that's just n times p times 1 minus p square rooted. So square root of n times p times 1 minus p, which is what they have there, but that's just 16. That's what I have here. Does that
Okay.
make sense? We want to figure out what z squared this corresponds to. 14.5 minus 20 is negative 5.5 divided by 4. Negative 1.375. So we're going to find that on our z chart. Eddie's my designated z chart guy. So this is the right hand part. That's okay. So we'll look for 1 point. Are you doing the left hand tail as well? A lot of people feel like, oh, I can't do the left hand tail in my head. It's just the right hand tail. Just do like 1 minus that or whatever, right? So you probably should have the right hand tail, right? Look
So-
for 1.375. We'll say 1.3. And we'll say right in the middle. 0.0853 and 0.0838 is like 0.842. 0.0843. So what that's saying is that this left-hand tail is 0.0843. What's the probability that larger or more? Yeah, 15 or more have missing pulses. So that would be 0.9157. And that's the answer. I hope.
Yep.
Cool. You might have small variances in the very tail end of depending on how much you rounded, right? Make sense?
Perfect.
Any questions on that? So this is almost guaranteed to be a question on your exam, that you're going to be converting your binomial distribution to a normal distribution using these formulas. And he might even just make sure you get an extra point, or if you make sure to verify using that formula 9 times the higher proportion over the smaller proportion. So make sure you check that assumption
Oh, it's
because.
negative this way.
Cool. Good. Any questions on that so far?
Okay, that's fine. True.
That's almost guaranteed to be a question.
Is there anything you wanted to specifically see, Ryan? Or
Actually, this next question was one that
Sure.
was a little tricky. And then
yeah, this was a 12-point question too. This one's worth the most.
Number 5. The following random variables are all dependent of each other. V is a normally distributed random variable. Holy shit. Okay. V is normally distributed. Mean 7, variance 16. He likes that variance of 16. W is a chi-square distribution with 5 degrees of freedom. X is,
remind me, I have some more to ask you after this.
sure, chi-square with 9 degrees of freedom. Y is chi-square, 10 degrees of freedom, and Z is the standard normal. Identify the distribution for each function of these variables given below. Each answer is a T, F, or chi-square distribution, and state the type of distribution and the values for the appropriate degrees of freedom. Okay. First one is, all right, when this problem's over, we are going to switch markers.
All right.
Z squared. Well, since Z is a normal random variable, 0 and 1, the Z squared is in a chi-square random variable, right? That okay.
Yeah, I could go
All
out.
right, sure.
I'll go extra round.
Oh, go to the front desk because a lot of the other ones are just. Go behind. Yeah, actually, was it? Grab behind there is one, I think.
Oh wait, there's one in the back? Okay.
Perfect.
Wow.
Oh, even better.
Thanks, man.
X has chi squared of chi squared of 10. Oops, no, it's not.
Okay. A chi-square random variable, let's say, a chi-square random variable, oh yeah. A chi-square random variable is the sum of the squares of k independent and identically distributed z random variables. What do you do, plus 1 or minus 1 for that? Okay. So how many z normals do I have here? There's just one. So that means this guy is distributed chi-square 1 degree of freedom.
Could you explain that definition again a bit?
Sure. A chi-square random variable is a sum of squares. I should say sum of squares. Sum of squares of k identically independent. Have you seen this before? IID.
Mm-hmm.
Just means independent and identically distributed.
Okay.
So it means if we had z, let's say zi, is distributed normally with mean mu, or not mean mu, but rather mean 0. This is the standard normal. If we did z1 squared plus z2 squared plus z3 squared plus z4 squared, then we'll call this, let's call this y. Then y would have the chi-square distribution with 4 degrees of freedom.
Oh, okay.
So since z is a normal random variable from that's the standard normal, and we're squaring it, it's just 1 all by itself. Then it's a chi-square distribution with 1 degree of freedom. Make sense? All right. B was 2w over y. Ugh. Over y. W is a chi-square random variable. Y is a chi-square random variable. This is where we have. This is going to be an F test, right? I believe.
Is that the proportions of chi squared?
A ratio, yeah, a ratio of chi-square.
Now, what I always wondered when you're going from this to that, like you have a chi squared with, like W is a chi squared with 5 degrees of freedom.
Mhm.
In the F test, that would be, like forget the 2, but that would be a chi squared or divided by 5, and then the Y is, chi squared divided by 10, but that's like, that's adding, you're like adding numbers. Is that just to show it, or is that, does it actually have to be divided by that too? You get what I'm saying?
I think I understand.
Like if I just go and divide, this whole thing by 2, then it's not like magically W over 1 and Y over 1. And
I think what you're thinking is this would remember. No, I'm not sure I know the answer to this one. At the very least, you know it's an F test, but then I don't know what you do with this too.
What's the question you're saying again? You're saying
so. Okay, so like what I'm confused on the F test is if the F test is like, let's say that like F is a chi squared divided by its degrees of freedom over another chi squared divided by its degrees of freedom.
yeah.
So if you had this, there are 2 chi squares over each other, but it's not being divided by anything. Well, I mean, I guess you could say the 2 is dividing the y divided by 2, but the y already has a chi-squared of 10 degrees of freedom, so I don't know how that changes
How the
it.
10 will work in there.
How that
Can you pull
would-
up F-test on Wikipedia so I can quickly read
Oh,
it?
what?
Wikipedia F-test, so I can really quickly have a look at it.
That's why I didn't know for F-test, is that like something for show, or like, I just,
No, I shouldn't be saying F-test, I should say F distribution, yeah, click that one.
I got that part right.
Keep going,
So W is that is a 10.
thanks.
What
Okay.
did
Random variable chi-squared.
Oh, okay, so I just did that by 1/2. But you could, I could multiply that by like 10 or 1/2, I don't know what.
Let's start with this.
Yeah, why is that one? Oh.
Because of this,
Gotcha,
but I
gotcha.
think what it is that
Okay.
this whole 2 doesn't even matter, it's just that this is all just a representation of it. I'm pretty sure for this it's supposed to be 10, so, by the way, the answer, do you want the answer?
Hold on a second, we'll get there. So this is an F, this is an F, right? So this is confusing, don't start here, start with this. We know that
Okay.
W is a chi-square random variable with 5 degrees of freedom.
Okay.
So don't look at this and say, okay, I know W is a chi-square, I know Y is a chi-square, so the ratio is an F. That's not quite right. It's W divided by S degrees of freedom and Y divided by S degrees of freedom. That would be an F test, right? So this would be, not F test, I keep saying F test, but that's, F distribution.
F
Yeah.
distribution.
Now, W over 5 and Y over 10 can be simplified. If I take Y over 10 and flip it and multiply that, it gives me 2W over Y. So I haven't really done anything to go from here to here. I haven't changed anything about this. It looks different, but it's mathematically equivalent to the one above it.
Okay.
So
it is
start with this
equivalent.
and go, oh look, it's just what we're being asked about. So the numerator degrees of freedom is considered 5. And I don't know how you write this. Sometimes you just say 5 comma 10. Is this what he does? Just signify.
Yeah.
Oh, okay, I added the 2 in there, okay, that's what I did.
Oh, I see what you're saying. You did W over Y and then you multiplied it by 2.
I put W divided by 5, then Y divided by 10, then multiplied it by 2, so.
But you wouldn't need it. It just
Exactly,
applies to this.
I didn't realize it simplifies to that.
Mhm.
That answers my question, because I kind of I was confused if it was a representation.
So this is
or-
confusing because you think to start with W over Y, you want to start with W over 5 and Y over 10 to get the desired
So-
test, but this simplifies
If
it.
we have 2 chi-squares, it's usually, I'm guessing it's an F, what's the T? T is something else, right? What's T?
Yeah, let's see.
Well, this one
T is- yeah, T is
this one,
just-
right?
Unless it's a Z.
Well, let's go on to C, which is X
Yeah,
over
okay.
9Z squared. Okay, I have no idea. X is, oh, it's chi-squared. Okay.
Yeah, it's chi-squared.
X over 9Z squared. Z squared would be what? What would Z squared be? Let's just write it down here on our table. Z squared would be what? What distribution?
It's a chi-squared of distribution 1 degree of freedom, right?
Exactly, degree 1 degree of freedom, right? So, let's start with X over S degrees of freedom, X over 9, divided by Z squared over, well, how many degrees of freedom does Z squared have?
1.
1. What would this be? This would be distributed how?
That's a F.
This is a chi-squared, right?
Yeah.
This is a chi-squared,
That's a F.
so it's an F.
That's F, okay.
With what numerator,
9
what
and 1, right?
9 numerator degrees of freedom, 1 denominator degree of freedom. Is this the same as this? Yeah, it is. If I flip this bottom fraction and multiply, the 1 moves up to the top,
Yeah, of course.
say times 1, and the Z squared occupies the bottom. So this is a F distribution with 9 numerator degrees of freedom and 1 denominator degree of freedom.
Okay.
Make sense?
Mhm.
We've got 3 times V minus 7. Ugh. 3 times V minus 7 over what?
4 times the square root of X.
V is a normal random variable. X is a chi-square random variable. This is, I have no idea. That's what I was thinking. This is what we said earlier though, right? Yeah. A T random variable is equal to a normal random variable over the square root of a chi-square random variable divided by its degrees of freedom. So this guy,
Okay.
oh, this all makes sense too. it takes a little bit of work. When you're talking about a t distribution, this has to be the standard normal. So this has to be distributed normal with 0, 1.
Okay.
By subtracting 7 from this random variable v, who has a mean of 7, what's the mean of v minus 7?
By subtracting 0.
0. That makes sense?
Mm-hmm.
Otherwise, this wouldn't work. And he's doing this deliberately. V isn't normal with mean 7 and variance of 16.
Mm-hmm.
If we do v minus 7 from a normal random variable that has expected value 7, then the mean would be 0, right?
Mm-hmm.
So this guy is going to be distributed normal with mean 0, but variance 16. Guess what happens when you divide by 4? What does that do to the variance of something? It's good to know. And these are some formulas you're going to want to know. Have you seen this before?
Yeah.
Value of x plus b. This is the same thing as a, we should say ax plus b. And the expected value of one random variable.
So then that's divided by, and then.
Right, well that's the variance, so we'll get there in a second.
So it's gonna go to 4.
These are the expected value formulas, and then the variance formulas are this. The variance of ax plus b is a squared variance of x. Notice the b doesn't go anywhere, the b vanishes. Why? When we're talking about variance, we're talking about the spread of a distribution.
Mm-hmm.
So suppose I have this distribution, its spread is, we'll say 49, right? Now if I
Okay.
step this way, what's the spread now? Still what?
49.
Right, it hasn't changed because I've shifted left and right. Shifting left and right doesn't change the spread of the distribution. That's why that b
Okay.
vanishes. This
Gotcha.
shifting factor left or right doesn't change the spread.
Mhm.
This factor of a does, it changes the spread. It's a multiplicative factor, so that changes the spread.
Okay.
So here's the thing. If I take the variance of, if I take a normal random variable, or take any random variable and divide by a certain number, it divides its variance by the square of that number. So what's happening? What happens when I divide this by 4? I can say, when I divide this by 4, it divides the variance by 16.
16.
Gotcha.
So this 4 goes away, and you could say 1. Make sense? That's kind of what's going on there.
Oh, okay.
Wait, I lost you for a second.
This was
So standard deviation.
this is the variance. The variance.
Is the, oh, that's the variance?
Right. If you divide the variance, if you divide a normal random variable by a number, its variance goes down by the square of that number. So what happens when I divide by 4? The variance will go down by what? A factor
okay,
of.
Okay. No. Yeah, I was actually getting confused because I was just getting confused for a second because I was thinking that its mean and standard deviation, not mean and
Right.
variance.
Mean and variance. Good.
Mhm.
Good enough.
Okay.
Okay. So getting rid of that 4 though will make that basically. We'll say this guy. This guy is distributed normal with mean 0 and a variance of 1, right? Which is, so far so good, what we want for a t. Now, what about the 3? Where the fuck does this guy go? Well, this guy's going to go into my denominator. Right?
And
Not-
here's the square root of 9.
Right, it's not quite in this form, right? But we're going to make it in that form by doing this.
Okay. Oh.
So now this is a standard normal on top, divided by the square root of a chi-square, simply an x chi-square, with 9 degrees of freedom. So this guy is a
T with 9
t with 9 degrees of freedom.
Can I take a picture of it?
Yeah, sure. You might still need to say mean. You still need a mean, I think. Maybe not.
Hmm?
Did you say mean? I think you get mean. Maybe not. Okay, never mind. But that's it. That's it for that problem.
Okay.
So let's kind of talk about what we have to do with these. We're basically manipulating algebraically, whether it be you're saying, well, a multiplication is really to divide by a division, or yeah, well, that's what I did with this 3. This 3 was here, but I'm going to divide it by a square root of 9. Or if I have a v minus 7, I ask myself, well, actually, you know what? The mean of this guy was 7, so v minus 7 would make the mean 0, stuff like that. Cool? All right. Any other questions on that one?
So it's a t is what are the sub things for it? Or the something sub
Subscripts?
This?
subscripts?
It's a T with 9
Oh,
degrees.
T, 9 degrees.
Yeah.
You saw how he got the 9 down
Okay,
there?
okay, because yeah,
Used to be a
there's,
three.
there's only 1 degree of freedom for the z, so that's the only thing that matters. Got it. Okay.
Yeah.
Cool?
Perfect.
All right, we move on to bias and MSE and stuff.
For the other question,
Yes.
Sure.
So.
For what, bias or the next step? Or are you gonna switching gears? Okay.
I think it's something similar.
Okay.
So for some of the proofs that you mentioned that might be on the exam are similar to this actually. So it's actually these are pretty easy. I think I can do these. But it's t squared, distribution t squared, the v degrees of freedom equals an f distribution with 1 comma v degrees of freedom.
Okay. So a t squared. Let's just start with t with v degrees of freedom. That would be a normal z, 0, 1, divided by square root of w over v. And we know w is a distributed chi-square with chi-square with v degrees of freedom. Now we're going to square both sides.
okay, yes.
It's actually pretty simple.
Yeah. Now this is what z squared? If z is a standard normal, what's z squared? Chi-square with 1 degree of freedom. And again, w is itself a chi-squared with v degrees of freedom. I should say, just the w is. So we have a chi-square, well, then you can say this is over 1. So this is going to be distributed as an f with 1 v. Pretty straightforward.
And the other one was, this one was a pretty easy one too.
Sure.
Prove that 1 over f distribution v1 v2 equals f distribution v2 v1. So that's pretty straightforward. You just that.
So an f distribution we'll say x1 is chi-square. Let's not use x, it's kind of confusing. Let's use y1. Let's just use y. Y is chi-square with v1 degrees of freedom, and w is chi-square with v2 degrees of freedom. Then f v1 v2 comma v2 would be y over v1 over w over v2, right? So then 1 over this just flips the guy, so you just get w over v2 over y over v1.
Okay.
Cool?
Yep.
Flip the entire thing.
Yeah.
Cool?
That's the only proofs he has related to that. So we come back to the other ones later.
Okay. The next problems are about bias and MSE, which are formulas that I have to brush up on, or I have to remind myself how to get those. Let me just briefly look at those.
So usually
Just in the
skip into
Okay.
this down there.
MSE equals the variance of the, let's say, MSE of some estimated theta is equal to the variance of theta plus the bias of theta.
Squared.
Bias of, which one's squared? Bias.
Bias of theta.
Okay. It's also theta hats. Technically, this should say theta hat minus theta according to the formula sheet, but if you square something that's reversed, it doesn't change anything. Okay. So we
That's
have
the MSE of theta hat, right?
yeah. Y1 through Yn be random samples in the uniform distribution. So Y1, Yn are independent, or I shouldn't say it's independent, but we're going to assume they are, I suppose. From each of the Yi's is from the uniform distribution theta comma
Same as
theta
homework.
plus 1.
Each one of these are all the same as homework.
All right.
We have a lot of work to do though.
Yeah.
Calculate MSE of y bar. Okay. You might want to know if I give you a random variable x that is uniformly distributed on a comma b, what's the mean? What's the expected value of x? Uniform distribution looks like this. A, B. Where's the mean?
Middle.
Right in the fucking
A
middle.
minus B over 2.
A plus B over 2.
Oh, yeah.
The variance, you can figure out using a formula. You've probably seen this formula before. B of x equals expected value of x squared
Yeah.
minus expected value of x. You're probably going to use this quite a bit in this class, but we're not going to use it now. You can use it to prove that the variance of this is, I believe, b minus a squared over 12 is the variance. I think I got that memorized.
I think he's gonna give us.
Yeah, I'm going to give those to you
He's gonna
right
give
now.
us
Yeah,
that.
but this
He
is
gives us the variance.
it's just nice to have those things fucking memorized. I mean, I didn't have to look at the formula that. I've been teaching this for a little bit, right? So I'm kind of cheating in that I've just been doing this for a while. But I mean, anything to save yourself some time, right? Anything to save yourself 15, 20
yeah.
seconds. There's just going to be, oh, I know that off the top of my head. Okay,
How many questions you say there's gonna be on the exam?
so far it looks like 10.
This
Or
is,
nine.
that was,
I know,
that was in class last year, now it's 2
Yeah,
hours.
he said.
Is it 2 hours?
Yeah, it's
Yeah,
a 2 hour
it's 2
exam.
hours.
Because that was a 15-minute
20
exam.
So why do you get 2 hours? How are you going to get 2 hours?
I used to be in class
Well, yeah, I think
last year. Now it's
we cover
now
more
it's
material.
So it's a
Yeah.
lecture, like one of those big halls
Yeah.
at night?
Yeah.
Oh, wow.
Mm-hmm.
It's going to be a big class. Okay,
It'll be fun.
so what is the mean of this distribution?
The mean is in theta.
Close, not quite.
The mean is gonna be
Theta
mu,
plus
right?
1 over 2, right? 2 theta plus 1 over 2, right?
Theta plus a half, right? 2 theta plus 1 all over 2. The 2 would cancel with the theta, but you still have an extra factor of a half, right? This would be right in the middle. Theta plus a half would be right between theta and theta plus 1. What would the variance be? Although I don't know if this would be relevant, we'll see. Probably not. Yeah, oh yeah, it is needed. B minus a squared over 12, but that would be theta plus 1 minus theta is 1 squared would be 1 over 12, so 1/12. So the MSE of theta hat equals the variance, which is 1/12, plus the bias. The bias is the difference. What's the bias again? The difference in, yeah, bias. Another point we might write down. Bias. Is that right? Am I missing? I'm missing something.
What's the expected value?
Expected value of theta. I don't know if I'm missing something. Now, what's the expected value of theta hat? We found it to be what? Or I should say
Yeah.
yi. Theta plus 1/2.
Mm-hmm.
But then minus theta. And we have to square this. So this is your, and then minus theta. Theta plus 1/2 minus theta is going to be what? 1/2. And 1/2 squared is 1/4. So this comes out to be 1/3. I think. 1/4 is 3/12 plus 1/12 is 4/12, which is 1/3. Is that the answer this guy got? Doesn't seem so. It doesn't look like he did much of anything. Oh, what does that depend on in? Oh, it does depend on in. Fuck a duck.
How do you do that?
Here's what I
Oh,
here's
we
what I
took,
got.
we have, it's supposed to be 1 over 12n.
Right. Okay. So here's what I found the effective value of just one of them. What's theta supposed to be?
You're supposed to,
Oh,
Y bar.
Y bar. We want an estimator for y. Yeah, an estimator for y bar. So here's what we're gonna do. You might have to show a little work like this. What would this expected